Our gun is, our electron gun is currently fully functional, and we already did some emittance tests, which you can see on this slide. On the left-hand side, there's an example for a DC voltage. Hello? Okay. On the left-hand side, there's an example for a DC voltage of 68 volt. Here we have a horizontal emittance of 12.9 millimeter times milliradian. Vertically, we have 8 millimeter times milliradian. The plot on the right-hand side illustrates the dependence of the emittance from the current of the focusing magnets and also from the DC voltage. Higher DC voltage means higher band charge, and this on the other hand means higher emittance, which can be seen clearly from the plots. Now let's have a closer look to our fell beam line. The first fell beam line, which is currently under construction, is the U35 beam line. It has a cavity length of 11.53 meter, and we will have two spherical shaped optics mirrors with a radius of 5.85 meter. Our undulator for this beam line was manufactured by Klima, and this one is already delivered, and we already did the on-site acceptance test. It has 54 periods with a period length of 35 millimeters. The minimum achievable gap is 18.1 millimeter. The design for our optical resonator was done by Traber. The design is completely finished, and we are now currently in the manufacturing stage. Our optical resonator will be suitable for wavelengths between 3.6 micrometer up to 37 micrometer. That's the wavelength the undulator delivers. The corresponding spot size is from 20 millimeter up to 71.6 millimeter. We will have 4 different outcouple mirrors with an outcouple hole from 0.5 millimeter up to 2 millimeter with 0.5 millimeter steps. The table on this slide illustrates the desired performance parameters. This is what we want to achieve with the performance of our optical resonator. Of course, we want to try to be as good as possible with a reasonable budget. Therefore, we also included some best support values for each axis, and we are quite confident that we can achieve them and that we will even be able to surpass 1 or 2 of them. Now let's have a closer look to our optical resonator. On this slide, we can see our M1 system of the optical resonator. This one will include the 4 outcouple mirrors. It will be a mirror slide on top of a cradle supported by 2 bearing blocks and a base structure. The mirror exchange, which is a translation axis, will be motorized, and we will also have a motorized pitch and roll alignment for each optic. The whole internal mechanic will be supported by 2 granite blocks. The lower, bigger granite block will support the vacuum chamber, which is currently hidden on the slide. And the upper granite block will support internal mechanics so that we have the internal mechanic completely decoupled from the chamber. Our pitch actuator will be a motorized wedge, and on top we will have a piezo actuator. In order to have a really stable system, we decided to get rid of any kind of lever. So we won't use any lever. Instead of this, we will support the V-shaped cradle on the strongest position, which is the tip of the V. And This has one disadvantage. If we get rid of a level for a rotational actuation, then we also lose some resolution. To compensate this loss in resolution, we included a PS actuator, and at the end, when everything is assembled, we will end up with a resolution of 3.2 nanoradian for the pitch alignment, which is 3 times better than the resolution of the retests. Our M2 system will just include one optic, and this optic will also have a motorized pitch and a motorized roll alignment. And this M2 system will also have the motorized alignment for the cavity lengths. All optics for the M2 system and the M1 system will be directly water cooled. We did some simulations to estimate the figure error of the optics, which is induced by the heat load of the beam, because in roughly 1.5% of the beam will be absorbed from the optics, and this will induce a heat-induced deformation of the surface. Now, according to our simulations, when you reheat up an optic which has a manufactured radius, then it will expand and we will end up with a new radius. The manufactured radius is 5,850 millimeter, and the heat-induced new radius is 6,150 millimeter. Now, when we subtract this new radius, then we end up with the surface deformation, which is the blue plot. The yellow plot is the corresponding slope error of this deformation, and the RMS of our slope error is 3.6 microradian, which is, in my opinion, quite good value for an optical resonator. By the way, this is for the worst case, which means this is for the wavelength of 3.6 micrometer, which has the highest power and the smallest spot size. Now our electron beam gun. We are close to be finished with the design of electron beam dump. Our first electron beam dump will be located in the accelerator hole in this corner here. Our electron beam dump we will manufacture it out of aluminum, and it will be internally water cooled. It will be protected by a layer of lead, and on top we will have a layer of concrete. And there are some tests open for the electron beam dump, which are currently running. When these tests are as expected, then we will finish the design of our electron beam dump and start the manufacturing. Now, of course, the priority for Tala is to finish our own beamline. But we also want to contribute to the accelerator technologies in Turkey. Therefore, we have projects which are run parallel to Tala. One example for this is the Turkish soft X-ray photoelectron spectroscopy beamline, short TEXPES. This one is located in the Sesame synchrotron in Jordan, and it will be build the branch B beamline of the it will build branch B of the HESET beamline. And Tala did the design of the whole beamline, and I assume that in 1 or maybe in 2 months we will have the FDR for this beamline and immediately start the manufacturing. The whole beamline will be assembled, and it will be assembled at Tala, and we will perform the performance tests also in Tala. When everything is as expected, we will take it and send it to Cesana and install it there. Thank you for your attention.
Baruch,
Yes.
I have a question. We have any described time schedule for the run of first UPHUKVIII to obtain the 20 MeV electron beam?
No, yes, we are planning to get our first 20 MeV beam close to the end of 2023.
Okay. Thank you very much. Do you have any other question or comment? If no, thanks to speaker again.
Thank you very much.
Our next speaker is Professor Ercan Özcan from Denmark NUKAN. He is director of NUKAN also. And Professor Özcan will give a talk on NUKAN status and plans.
Hello, can you hear me?
Hello. Yes, we are hearing you.
Would you like me to share directly from my screen, or would you like to open the slides and
I think you can share your slide yourself.
Okay, let me try that immediately.
Host olarak tanımladık değil mi arkadaşlar?
Yes, I think I should be able to do it.
Okay, you are ready.
Okay, good afternoon, everybody. I apologize, I have not been able to come to the meeting in person yet. I will be coming on Wednesday morning, so if you'd like to chat about what I'm going to talk about today, I'll be available as well. Today, what I'll talk about is a brief summary of what NUKAN is doing, Nuclear Energy Research Institute is doing, and how it wants to proceed in the coming year or so. As you know, the Turkish Atomic Energy Agency was restructured, just a minute, was restructured in 2020, and it became TENMAK after the inclusion of the Boron Research Institute and the Rare Earth Elements Research Institute. The R&D parts of Turkish Atomic Energy Agency became NUKAN, the Nuclear Energy Research Institute, and two other institutes, one for clean energy and the other one in general energy policies and new energy sources have been established. Overall, the full TENMAK body has about 850 personnel, about 60% of which is at NUKAN. Now, TENMAK is an overall R&D agency, much like the UPHUKVIII. You can consider it roughly equivalent of the Office of Science under the Department of Energy in the United States, if you are familiar with the funding agencies of the United States. And as an R&D institute, it develops strategy, carries out the research itself, funds it, and facilitates it. Under this big umbrella, TENMAK is essentially four kinds of different, it has four different phases. The first one is it is a place to run big science and fund big science, including CERN and Sesame projects and accelerators and research reactors in Turkey. It's a technical support organization for various branches of the Turkish government, including the Nuclear Regulatory Agency, this NDK, and Ministry of Culture, and all kinds of customs, security, forensics, various agencies. Radioactive waste management is under the purview of NUTENMAC, as well as it functions as the head of radiological metrology in Turkey. NUKEN is located in 2 campuses with about half, 40–60% of its staff distributed in Istanbul and Ankara. The Çekmece campus is the well-known campus from 1958. Its research mainly focuses on nuclear reactors, fuels, waste, and related technologies, whereas the Sarayköy campus is focused on accelerators, irradiation, and detector technologies. Before I move on to what the current status is and what the plans are, I'd like to give you an idea about what NUKEN does, because until I joined the agency about a year ago, I was also unaware of the breadth of research done at the Institute. And the reason I'm just listing these things is because I also want to emphasize that the new TENMAC vision is to open up the gates for maximum collaboration with the academy and industry. So if you know of what is being done, this might also give you an idea of what we might collaborate on. On the right, you see a selection of our services on radiation metrology, dosimeter services, biological dose determination, and all kinds of irradiation of spices, medical equipment, etc. We have this one of the 2 such facilities in Turkey. Identification, emergency preparedness, and of course, auditing of various therapy and imaging devices. And the projects, example projects, include the beta voltaic battery, boron-10 enrichment through chemical processes, internal confinement, electrostatic confinement based deuterium fusion reactor, radiation early warning systems, and various radiation monitoring systems throughout the country, and various nuclear agriculture projects. Mutation breeding is just only one of them. Various research on improving the efficiency of watering, and I don't know, how to increase the use of soil, etc. These are all within our research fields. This is an example of those, the beta voltaic battery. The first prototype was built in 2018. As you know, these are devices which never get charged. You just have stable running time that is comparable with the half-life of whatever beta source that you deposit on it. I wanted to show this because this is an example of a collaboration with Nanotam. And we have some facilities to work with silicon-based devices, and we are happy to collaborate with Turkish academia on this topic. One example of what's going on is that is done inside the institute is next generation transparent ceramic scintillators. You can see examples of this. The red ones on the table are what are produced within the institute. We have not yet reached the target resolutions that are listed in the table, but we are below already 7% or so. So comparable to sodium iodide, thallium dope. You can see samples of these transparent scintillators on the right side of the page, as well as a device that has been entirely built in Turkey, including the scintillator, the circuits, electronics, Bluetooth, and other network communications, everything essentially. This device is going to be this new generation of gamma dose rate meters from NUKEN. And what you see in this picture is just a 3D printed prototype of the casing. We are going to have a stylishly designed casing, and we hope to have that available in 2023. Speaking of scintillators, you know that over the years, TAEC had produced plastic scintillators. There is an experience going back more than a decade now. Some of the recent samples have been sent to test at CERN, for quality tests at CERN, and they went through with flying colors. And what is more kind of recent in the last year is that we have started producing large blocks of these scintillators. The picture that you see on the top right is a block of more than 1 meter in length. And the goal, of course, initially is to produce these blocks and use them in the radiation tracking system, RIS systems that are located around 300 locations in Turkey. The scintillators, we used to buy them from Czech Republic, and now we'll be able to produce them. We are happy to collaborate on scintillators with the academia. We have provided some test samples to a number of laboratories, and we'll be happy to work on more. Speaking of scintillators and circuits, and this is an example application of what was done at the institute over the last 6 months, and an overall detection system was implemented. All the power, communication, and buffer, scintillators, different kinds of scintillators, they are all put into one compact package that can be easily installed under a drone. The total payload is around 4.5 to 4.7 kilogram, and the software to track, control and track the data has also been written in-house. This is another news. The institute has been working on a Geiger-Müller tube production system. What you see on the right top is the gas filling system, and this takes up to 5 different types of gases, mixes them with the right proportions that can be easily programmed on the fly, and after the mix is done, it fills up to 4 tubes in parallel. This thing has been commissioned. The filling system has been commissioned. Mixer and filler has been commissioned. What we are working on is that the tubes themselves, a process and another device to anneal the glass to the steel is being worked on, and if this is successful, we'll be able to produce Geiger-Müller tubes for various applications in Turkey, including the dose rate meters, dose rate meters that are being sold under the Tenmak brand for many years. You can see that the tubes have the gas properly filled. And when you excite them, when we excite them with sparks, you can see the plasma forming inside the tubes as we expect. Next, I'd like to talk, say a few words about the electron accelerator facility. This is yet another facility that our community is familiar with. It is half MeV up to 20 milliampere electricity electron accelerator that was used over the years for as a demonstrator of flue gas treatment. And recently it was modified to treat wastewater from hospitals. This is a device that is rather old, but it has gone through some repairs over the last couple of months, and we hope to publish results about its facility, its ability to clean various microbial load from hospital wastewaters. What I'd like to mention here is that there's an upcoming workshop in collaboration with the Atomic Energy Agency in about a month and a half. This will be in Ankara at NÜKEN, and it will have two sessions, two parts. In one of the parts, we have started inviting industrial partners, including possible consumers like municipalities in the big cities of Turkey, and we want to bring the academia and industry together to make clear that the industry needs these accelerators, and to show that the Turkish academy has the ability to deliver such devices. So if you're interested in also showcasing your work and to find out possible consumers of products, accelerators that you develop, you are more than welcome to join. Another project that again our community is familiar with is the RFQ project, SANEM project Prometheus, the project that runs at 352 megahertz, and to get protons from about 20 keV to up to 1.3 MeV. This project is, well, this accelerator is now being is now to be upgraded to run in some sort of stable mode, and hopefully for applications for applications like particle induced X-ray emission and Rutherford backscattering. So that's the news about this one. The proton accelerator facility, the workload, the main workhorse for the full facility for the institute, as you know, is a cyclotron from IBA, a 30 MeV cyclotron from IBA with up to 1.2 milliampere current. Over the years, you know that TAEC and now TEMMAC has been producing a number of radioisotopes to be used at the hospitals. In particular, we are still supplying and selling to various hospitals thallium-201 and sodium-123, and some of these has started some of these products are now also being important to foreign countries, and what is real news with this is that a good amount of radiochemistry work went into developing an in-house way to produce gallium-68. unlike previous radioisotopes, the full know-how is now domestic, so it's our in-house development. And about 2-3 months ago, we have successfully synthesized gallium-68 and sent prototype samples, test samples to 2 companies. We sold actually to 2 companies, and the results were very positive. So in the next year, we want to start using the facility 7 days, 24 hours to produce gallium-68 and sell it to multiple companies. If you're interested, please let people that you know learn about this. Okay, so that's it. Moreover, those who are connected to the nuclear medicine field in academia, this is also a call to them. We would like to be at the forefront of developing new radiopharmaceuticals, either for tests or for full production. And we are happy to accommodate such proposals. Another thing that's going on with the Proton Accelerator facility is that the R&D irradiation room is now being redesigned to be some sort of autonomous room. If you'd like to test samples, if you want to irradiate samples, if you'd like to work on new detectors or beam diagnostics equipment, we will make sure that you will be able to enter the facility without going through the full hoops of you know, if you want to go to the facility, you need to go into these coveralls because of the regulations from the Ministry of Health. Now you won't need to do that. So we hope that we will get more collaborators from the academia coming and using this R&D irradiation room. An example of such collaboration is with the Middle East Technical University, Department of Metallurgical and Material Engineering. As you know, the upcoming 4th generation nuclear reactors and also like fusion reactors have very demanding constraints on the material in terms of temperature and also in terms of the damage to the material measured in terms of displacement per atom. The EPA is essentially the number of times an atom is displaced from its original lattice position. You can see that, for instance, for molten salt reactors, upwards of 100 dPa is expected. The same is also true for instance, sodium cooled fast reactors. And we want to develop, well, as not only as NUKAN, but not only as Turkey, but in general, in the world, we would like to develop new materials that can withstand such a harsh environment. And for this, whatever the materials are developed need to be tested. And this new project in collaboration with METU hopes to simulate the neutron damage using the protons that we have at the Proton Accelerator facility. An example, a motivation for this comes from this example at Texas A&M University. They have this 1.7 megavolt tandetron proton or heavy ion source, and they are doing these sort of tests. So our aim will be to get down to a couple of MeV and then produce the beam in a way that is conducive to doing this sort of research. And we will produce and test new materials. So this will be cutting edge search in material science. Okay, let me conclude by saying that TEMAC has been taking indeed concrete steps towards restructuring itself. It wants to be an agile agency that actively listens to academics and forges long-lasting and enduring sustainable collaborations with industry and universities. And it also aims to be a reliable supporter of big science. With this new vision, we welcome opportunities for all sorts of collaboration. And in particular, of course, we are looking for any applications of the 30 MeV proton beam and its possible upgrades. So if you have ideas on how to increase the 30 MeV, produce new accelerator components, or use the 30 MeV beam for any sort of basic or applied science. So for instance, if you like to measure, I don't know, some cross sections that has not been measured over the years in the literature, or you want to produce new radioisotopes that can be used for various applications, we are more than happy to hear your opinions. That's it. Thank you.
Okay, Professor Özcan, thank you very much for this nice talk. Any question or comment about talk? Okay, Gökhan.
Yeah, hi. I saw that in the radiation scanning application with the drone, the locally produced scintillator was directly coupled to a phototube. You don't use a light guide? Do you produce a light guide? Did I misinterpret what I saw?
No, you're right. You can actually see the phototube connected to the scintillator. Since we were constrained by volume and weight, and we did a number of studies, and we found out that using this way with some sort of grease in the middle, of course, to make a better light contact, this worked fine. But I have to say this is only the first prototype. All the structure is 3D printed, and we would like to do some optimizations on this later on. So you're right, it would benefit from a light guide if we can adjust for the weight and size.
Okay, thank you. Another question or comment, please? Okay, if there is no any additional question, thanks to speaker again. Thank you, Professor Özcan. Okay, our our next speaker before the coffee break, Associate Professor Aytul Adıgüzel from Istanbul University. She will give a talk on Kahve Lab status and plans.
Hello. Okay. Tamam, mouse şey nerede? Teşekkürler. Hello, everyone. So I will give some information about Kahve Laboratory status and plans today on behalf of Kahve Lab. Ayberk hocam. Yeah. UPHUKVIII Lab is a particle detector, accelerator, and instrumentation research laboratory located in UPHUKVIII that you see from this picture. And it's the building it's in the Boğaziçi University Kandilli Observatory campus. In addition to the Boğaziçi University, our team consists of and closely collaborates with researchers from a number of institutes from all around Turkey. Like me, I am from Istanbul University, and you can see the all institutes that we collaborated in here at the top. And we built a number of particle detector and proton and electron machine aiming kiloelectrovolt and MeV energies, all with local resources. And we are also conducting our research at CERN on experimental particle physics as a member of the ATLAS experiment on LSC. So here is the actually outline for today. First of all, I would like to explain the kahve meaning. So it's an acronym of the Kandilli, Algıç, Hızlandırıcı, and Enstrümantasyon. Actually, the name was chosen by all members of the laboratory. So it got the highest point when it was chosen. So our outline consists of three main parts: the accelerator part, detector part, and instrumentation part. In the accelerator part, we have also three subsections: proton, electron, and RF part. So here is our team that are coming from the different university. Actually, we couldn't find photos that had everybody in it. So probably we missed photos of a number of people and apologize to them. And as you see, we are nearly 30 people. We are working together and collaborated. And all actually, we would like to also thank to our younger students. They working really hard in our laboratory. So first of all, I will talk with the electron part. Actually, electron part has been presented and also discussed a lot of times in the past, in the previous edition of the Congress. So I'm not going to spend too much time on it. And also my colleague, Ümit, he will give some detailed information about it on Wednesday. I think it will be in the first session. So it's designed and manufactured locally. Actually, it's a springboard project, and it's designed with the CST simulation. Actually, but I need to emphasize a few points. We have tested a number of ideas. For example, typically we start working with the tungsten, and then we realize that thoriated tungsten is better at the low temperature. Also, LaB6 gives a lot of electrons that has been tested too. And also dispenser cathodes is useful in other areas that has been tested again. So here is our high voltage setup, and you see the cathode part, then anode part, and the vacuum chamber here. So for the safety, we use some insulators like alumina, PEEK, and Teflon. We are using the Teflon, it's the shining one in this picture. And we control and monitoring the beam remotely via Bluetooth and Wi-Fi. And we also produce our magnets like stirrer and focusing. And also we control the beam automatically using the PID controller. Actually, after we had a lot of grounding work, we had a stable operation. Now it's ready for the other projects. And on the left-hand side, you see our power supply units and vacuum rack. So when we move on the EGAN application, actually we did some studies on the electron beam welding and hardening. So on Wednesday, probably you will see the more details about it. So again, here is our setup and cathode part and anode part, and we have the coils to center the beam, and we have the two coils focus to beam, and this is the vacuum chamber, and it can take the cylindrical objects of diameter 10 centimeter and also the height of 20 millimeter. Sorry, 10 centimeter and 20 centimeter, and here is the vacuum pressure. It's 10 to the minus 7 millibar, and also this thing has 2 degree of freedom that you can rotate. And here is some application done by laser, TIG, and electron. Actually, in this tool, we have some oxidation issues. So as you see, the electron, the beam electron is the better results when we compare the others. So also, my colleague also, they did some studies, electron beam hardening. So by changing the energy on the sample that you can see here, so we can manage to get something like 30% surface hardening with the stainless steel 304. So with the support to UPHUKVIII and Boğaziçi University, we built electron gun and electron welding. Now we are preparing a rhodotron prototype to raise energy to the MeV level. So the idea is following. Actually, you have a set of 2 concentric circles inside and inside and outside. The electron entered here, and they moved along the line. And if they are accelerated if they move with correct RF phase. So it is a multi-pass machine actually. So we completed 1 MeV machine design, and now we are working on the dedicated software. And our construction is still ongoing. Actually, as you see from the top, we had some initial setbacks, and we are planning to finish our vacuum test by summer. And we are planning to have the first beam in 2023. So for the next part, we will finish the rhodotron. Then we are focused on the electron beam microscope, and we are trying to accelerate electron beam into air, and then we move on to X-ray production. So after the electron part, I would like to move on our proton parts. So here is our proton test beam line at Kandilli. Actually, the project aims to design and produce a radio frequency quadrupole operating at 800 megahertz to accelerate 1 milliampere and 20 kilovolt electrovolt energy proton beam to the MeV. So it's intended to be 1 meter long. And in here, the exit energy is given as 2 MeV. So here is our schematic line. We start with the power supply units. Then you see our ion source units. And then Levitt line, low energy beam transport line starts with including 2 solenoids, 2 stereo magnets, and our diagnostic station. Then you see our RFQ cavity itself. So what are our goal? Actually, we are trying to educate our students for accelerator physics, and also we have a lot of engineers our lab. And the other main goal is to accumulate operational know-how. So all components that you see in here locally designed and manufactured in tandem with the local companies. And also the other purpose of the project is to be a particle accelerator technologies test setup such as PIXE. So here is our proton test beam line at Kandilli. Here is our setup, whole setup. So we have magnetron, 2.45 gigahertz microwave power supply in here. And here is the waveguides. Then we have ion source with the electromagnets. Then our extraction system starts. Then here is our Levitt line we have 2 solenoid, 2 striated magnet, and measurement box. Then you see the RFQ in picture, but it's virtually seen. So actually, the current setup, the previous setup includes the ion source with the electromagnets. So it designed with IB simulation, and the exit energy of the ion source is 20 kilovolt. And we use Teflon and Darlene as an insulator. So the vacuum pressure is 10 to the -7 without beam. And we can also control the waveguide power via magnetron power control. And it's possible to monitor transmitted and reflected power. And so since we use the electromagnets, they need to be cooled by water. And according to our simulation results, at 1.3 milliamp current, we have normalized emittance nearly 2.5 nanometer. And actually, we had operation in fourth quadrant of the 2021 and first quadrant of the 2022. Then we move on the microwave ion source with the permanent magnets. Why we move on the permanent magnets? Because, as you know, the electromagnets are good, but they may occasionally cause the sparks between solenoids and plasma chamber. And they also need the cooling because of ohmic losses and the plasma chamber's heat. So the permanent magnets are better. They can keep under high voltage, and they do not require additional power supply units. So instead of electromagnets, we use 32 and 40 type neodymium magnets. And here is our operation parameter: gas flow, the voltage, pressure, vacuum pressure, and the current. And on the right-hand side top, you see the permanent magnet MDIS design with the plasma chamber. The blue one are permanent magnets. And on the left-hand side, you see the field measurement setup for the trial production. And on the right-hand side bottom, you see the obtained beam image from fluorescent screen placed at the end of the PMMD system. And in here also in the middle, you see our magnetron circuit and waveguide transmission waveguide system. And as you see, we have hydrogen plasma visible in pink at the end of the waveguide line. And at the bottom, you see our beam results, and Faraday cup through the oscilloscope is found as 0.38 milliampere, and the difference is about 80% with respect to high voltage power supply unit. So let's move on to our low energy beam transport line. As you see in here, that I said before, we have 2 solenoids and 2 stirrer and beam diagnostic station. And in here, you see the output of our software Demirci results. Actually, the picture of the outputs from our software simulation. And the dot line corresponds to, actually, this is the RMS envelope. And the dot line shows the 10 sigma, and while the inside dashed line shows the 1 sigma. And we have also some simulation results from the Demirci Pro. You see the beam profile at the top on the slide on the right-hand side. And the 1 sigma is correspond to 16 millimeter in here. And in here, you see also our RMS radius of the beam. Again, the big one is corresponds to 10 sigma, and the other one corresponds to 1 sigma. And here is you see our beam loss. So when we focus on the measurement box, we have 3 detectors inside, and the one of them is the pepper pot to measure beam emittance, and the second ones is used to measure beam profile and beam shape, and also the last one is used for the measure beam current. So the photo is taken from here. You see our whole M-box measurement box station, and after we took the photo, we see the beam. We have the beam shape, and then we analyze it. And on the right-hand side bottom, you see the particle density in the X and Y axis. As you see in the yellow line, the beam diameter is nearly 16 millimeter. So it's compatible if you go back to look our Demirci Pro resolution. So they are compatible together. So we did some measurements at different places. For example, here you see the beam results inside the measurement box, and the results coming from at the end of the Levitt line, and you see the beam results in here in the scintillator mask after passing through the paper pot mask. And here is our signals from Faraday cup in here. And we also obtained our parameters for the simulation and measurements. And they are actually nearly compatible, except one of them. We are still working on it. So then our RFQ, it's at the end of it's after the Levitt line. So as I said before, we aim to design and produce a radio frequency quadrupole at 800. So the output energy is 2 MeV, as you see in here. And actually 2D and 3D simulation is performed by PalmTech and the other simulation software programs. And we also checked all of them. And we would like to have actually 2 modules, but in here you see our module 0. This is the prototype from Cooper, produced to finalize the manufacturer producer. We completed its vacuum and electromagnetic test and is mounting 18 plus minus 1 micrometer. So vacuum tests are finalized in Ankara that are done by our colleagues from Ankara. Lowest value reached by the two turbomolecular pumps. It's here nearly 2.8 10 to the minus 6. With the 3D O-ring, we achieved the 10 to the minus 6 millibar. So after vacuum test, we also electromagnetic field test and measurements were carried out using bit pool setup. You see our bit pool setup, and in here you see our tuners. According to simulations, in case of all tuners are flash, the frequency of the quadrupole, it's nearly 780 megahertz. And here is our quality factor. And for the simulation, it's nearly 7,000. And for the measurement, it's nearly 5,900. And also the coaxial combiner is designed for the RFQ in here, as you see, using the alumina material. And maximum power transmission and minimum loss power were obtained from the were obtained for coupler design and designed according to the simulation as parameter results in here. Also, my colleagues, they had some studies on the effect of the surface roughness for the different mode. And as you see, nearly the level of 50 micrometers, the quality factor is dropped, but it's not too weak in here. So for the proton part, if I finalize our status and plans, ion source and Levitt line are installed and they are being commissioned. And now on, we are using the permanent magnet ion source, and beam measurement station is now fully automated. For the RFQ part, as I said before, the copper module 0 is produced and tested, and oxygen-free electric copper modules 1 and 2 production will start in coming weeks. And we are planning to install it in end of 2022. And we are planning to do our vacuum and RF training test in quadrant of 2023. And we hope to have first beam in quadrant 3 of 2023, depending on our RF power supply status. So let's move on to RF part, the last part of the accelerator part. And so we run to these machines, we need power. So 2D and 3D simulations are done by Poisson Superfiche and CST respectively to calculate quality factor and p-wall. And the operational frequency is nearly 100 megahertz. And we need, as far as we see from the simulation, we need 50 kilowatt total power, and we are planning to merge our RF power supplies. So what are our status on that part? All power supplies is individually tested, and we'll use coaxial, we will use the coaxial transmission line, and also RF signal generator and preamplifier are tested, and we also tested our remote control. Actually, you see in here our low-level RF test. We couldn't move the high-level test since we need a good RF load. And also we are trying to finalize our design. We are trying to decide some issues, for example, 3 dB adder or feed cavity in 2 places, or we need to check the coupler design. And also our colleges needs to do some study on the multifactoring verifications. So then we move on the proton part. We need power also this part, and we calculate the power that we need using the ParmTank and Demergy Pro software programs. We need at least 50 kilowatt power, but we should consider also safety factor and RF power supply efficiency, and also 2% duty factor, so that we include all of them. The wall power is needed nearly 5 kilowatt amps. And we have received 2 RF power supplies as donation. Here is the name, the tetrod's name in here. And maximum power delivered by the TH582 is 35 kilowatt in pulse mode. And we are planning to use the Magic T to combine RF power. And as you see from the right, you see that our power supplies are being rejuvenated. So when we move to our transmission line in this slide, you see the schematic one and the design one on the right-hand side. And we combine power to cavity via waveguide circulator. Actually, we convert it, then combine it, as you see from here. So this is our transmission line in the laboratory. So we have some tested on signal generator, solid-state preamplifiers, also circulator, waveguides, and RF loads. And as I said before, we plan to use Magic T to combine power. So until now, I talked about our proton, our accelerator part. So now I will move on to our detector studies. So actually we built our own delay wire chamber to measure beam position in 2 dimensions. And we also tested it in the extern on the beam line. We obtained a successful result from this study. And we have also, as you see, the Faraday cup in here. And we have some scintillator counters. And as you see from our measurement box, we did some beam measurement study. And now we move on to for the electron part, scanning electron microscope studies. So here is our ongoing projects: electron beam microscopy, TC vacuum gauge, beam monitor screen. Actually, in our lab, we use a homemade fluorescence screen. We had more experience about it. Now we are trying to another option by, for example, using the alumina. And for the controller, Wi-Fi and Bluetooth voltage and current. They are also our ongoing projects. And also we are planning to work on the current sensors. So for the instrumentation part, actually, that I said before, we need magnets to focus the beam and to center the beam. So we are using the Stirrer magnets for the two machine actually. And here is the Stirrer magnets for the electron beam line. And here is the Stirrer magnets for the proton beam line. And we have also coils. They are produced locally, and they are manufactured in local companies. So when we focus on the measurement box station for this issue, first of all, you have a vacuum chamber, as you see here. And also in the measurement box, we, as I said before, we have 3 detectors. So in order to measure beam features, we push the detectors using pneumatic cylinders in here, as you see. And here is our picture from the vacuum setup. And measurement box had good vacuum. With beam, we have nearly 2 10 to the minus 5 millibar. And without beam, we have 1.3 10 to the minus 6 millibar. And here is our system when we do the vacuum test in here. And on the right-hand side, you see our paper pot that are produced by UPHUKVIII. And thanks to them again, we are also collaborated with them. And in this time, they really help us all the time. So also we did another, we also did some studies, another studies in the laboratory. For example, we have 3D printer. Actually, if you have 3D printer in your lab, you can save the life. So there are some example that you see from that you see here in this picture. We are also did copper coating in here, as you see, and we are also some. We also need. We also use some stuff for the shielding of our ion source, and also when we move to, for example, in here for the cooling system, we again use the stuff from that are produced by the 3D printer. So controlling the beam, as I said before, we can control the beam using LabVIEW and PLC and U controller. So based on the Arduino, of course. And also there is a fancy thing like other applications, the possible applications like electron beam lithography. So as a summary and outlook, UPHUKVIII Lab aims to have MEV level electron and proton beams by 2023. And we have a milliamp beam current. And in this time, we did educational and application studies in our laboratory. And also we tested our detectors on the beam, and we had some instrumentation and readout system. And our detector, we have also gases detectors like delay wire chamber and scintillator detectors, as you see from our measurement box. And all components are developed and produced locally. And of course, we are looking for collaborations. As you know, there are things that we didn't know, we couldn't know. So we need to collaborate for the other people. So we also need the people and qualified person power. And also, as I said before, it's important to know and how for building stuff like alumina and ferrets. So thank you for attention and listening.
for this nice talk on Kahverat studies and projects. Nice. If you have any question or comment, you can get.
Our members inside, the Kahve Lab members, so they have already known our structure.
I have a small question.
Yeah, sure.
Can you explain about the funding structure of Kahverat?
Yeah, with the support of TÜBİTAK and Boğaziçi University and Istanbul University, we have kind of funding.
TÜBİTAK and BAP
Yes,
supports.
BAP,
Okay,
the local sources actually.
very nice, and different projects are going on.
Yeah.
Thank you. Okay. Mikrofonla.
What?
With the microphone. So is the RFQ you design and produce, is it the highest in the world
Yes.
still?
Yes,
Do
it's
you
greater
check
than the
if
CERN
somebody
one.
else is buying somewhere in the world? Because it is very good for
As far as I
technical.
know, no. This is the highest
Okay.
RFQ in the world now, for now. So is there any question?
Is there any main differences between TAEX and your RFQ structure in frequency or structure, you know?
So I think the soruyu tekrarlayabilir misin hocam? Can you repeat your question?
Okay. Is there, okay. Is there any main differences between TAEX RFQ structure and your Kahvelab RFQ structure in frequency or geometric shapes, etc.? I don't know.
What are the difference
RFQ structure.
RFQ structure between TENMAC and our laboratory?
Yeah.
The frequency
I
is
saw the energy level is the same.
the output
have-
energy
yeah.
we have 2 MeV.
2 MeV. They have 1.5.
Yeah.
Okay. Okay. Mhm.
Maybe you can give the microphone to your camp, since he is
Because
working
it
for
is-
them.
It is a very big success.
The frequency is the difference, one. And the beam dynamic design is whole difference because the 10 Mach RFQ designed for 100% transmission for different applications. And this RFQ is designed for the short.
So he said that's all.
Okay, I understand. Thank you very much for your contribution. If there is no any other question or comment, thanks to speaker again.
you.
Now we have 20 minutes coffee break. And we will start at 16:35.
Onun pili bitmiş olabilir. Çalıştı mı?
Ah, geldi. Ses.
Evet arkadaşlar. Hazırsak başlayabiliriz. Başlatayım mı?
Hello, everyone.
Okay.
Can you hear me?
Welcome, Dr. Ashan. We are ready to start. Are you ready?
I am very ready.
Okay. Now, in this session, we have two speakers. The first speaker is Dr. Ashan
Yet
Bajak
I don't know if you are receiving my.
from Tarla in Ankara, and he will give a talk on Tarla applications and users and ISL laboratory.
Hello, everyone. Can you hear me?
Yes, we are hearing Dr. Bajak. You can
Perfect.
start reading.
Can you see my screen? Because I can't see the shared screen with you.
Okay.
Can you see my full screen?
You can share your presentation at first.
I can't unfortunately find the sharing option right now. Give me a sec, please. There you go.
Find as post now. You can share now, I think.
That's it. Are you with me now?
Yes, we are hearing you.
Can you
But
see my screen as well?
Yes, we are waiting for your presentation to see.
I am sharing my screen, trying to.
At first, you will choose Ekran and then share.
Screen share. There. That's what I'm trying to do.
Now we saw your slides, Doctor.
Were you seeing my slides? That's my unfortunate problem right now. There you go.
Okay, now your slides are ready to presentation. You can.
Perfect.
Yes, okay, you are ready.
Thank you very much.
Okay. You will have 30.
Today's talk, everyone. Thank you very much, sir. I think I have 30 minutes.
Okay.
Welcome to today's talk. I am Dr. Ashan Bajak. I moved to Turkey from University of Manchester about a year and a half ago. Today's talk will be presenting our laboratory that we are setting up in Turkey, Turkish Accelerator Radiation Laboratories in Ankara with my research group. This research has been carrying on since the beginning of my career of 24 years. Today's talk mainly targeting to explain from my perspective how such infrastructures like accelerators are in use all over the world. Thank you very much for the previous speakers that they explained so much about accelerators and the accelerator technology. Of course, this is a immensely growing field since the beginning of 19th century. Early accelerators we built in 1905, 1907, 1903. since then, we have been improving this technology. Yet, when we build such great ability and infrastructures, that how we going to use these infrastructures for the knowledge collection of humanity. Part of what our laboratory is doing is this. I am an expert on reaction kinetics, and we will be showing some of our research results today to you. What kind of research we are leading and what kind of research we are planning to establish in particle accelerator in Turkey, in Ankara. In this slide, you are seeing at the bottom left-hand corner my personal luggage. That's 3 tons of sea container. That's where I brought my, and you are seeing my field deployment measurements of North Pole, the research aeroplane of ENCAS, which is an English body of atmospheric research, and from Amazon rainforest, and in my Tarla office, and my group members with 2 masters and 2 star bursary students from TÜBİTAK, and some exchange students. My first slide is 6 random guy. Well, actually 5 random guy and a moon crater. All these guys are personal favorite person, Abu Reyhan Al-Bruni. All these guys took the challenge of proving that we are living on a spherical shaped object, and the target of the Pythagoras of Samos is possible on a spherical shaped object. Then Plato have taught on the subject and did some observations over the shadow movements of the objects, and taught that yes, we should be living on a spherical object. Aristotle followed the Hello, everyone. Hello. Can you hear me?
Hello, Dr. Ashan.
Yes, I am sorry. I think I lost my internet connection.
Okay, we are ready to listen. Yeah.
Perfect.
Okay.
So Eratosthenes that we were talking about, I hope you heard that part. Just by using shadows, moving shadows on Earth, he calculated 40,000 kilometers circumference, which is about 10% error to today's measurements that we are doing from space. And then science traveled from European land to Arab Peninsula. And Al-Mahmoun, that we can't see his picture or a buste. I don't know why, because of the time, or maybe that was because of he was a caliph. He was a caliph at the time, at 830 AC. He made a great deal of calculating the circumference of the sphere that we are living on. And his student, Al-Biruni, managed to calculate just by using some trigonometry, more than Aristotle's. He calculated with less than 1% mistake, error, 44,000 kilometers. Today we are calculating, or we are observing 43,700 meters or something like that. So these geniuses, just by using information of angle and length, did calculated the circumference of the object that they are living on. They don't even have a thought of what kind of an object this is. So this is always my inspiration. This little slide is always my inspiration of how we should pursue science and how we should work on science. Now, when we come to our expertise subject of atmosphere, this is again one of my favorite slides from NOAA, National Oceanographic and Atmospheric Administration of America. What you are seeing here is not just our system, our alive system of atmosphere. What you are seeing here is the most complex mathematical relation that humanity right now is trying to understand. Prior to this picture, our hardest mathematical problem is to understand was DNA chain. Following the mapping efforts of DNA, Human Genome Project, we worked on how to understand the mathematical relations of the long 1.5 billion characters code. Now our new challenge is to understand this system, such an unstable system, and it's real time in mix. So many different effects from outside, from inside, from within, of mixture effects, so many different phenomena, such as lightning, such as sun shining over, such as day and night. All the chemistries are different, oxidation pathways are different, aerosolization, volcanoes, human activity, industrial activity, oceans, animals, wildfires, and all these within mix. What, at this point, maybe we should understand an important question. What is understanding of a phenomena? How we understand a phenomena that is not understood yet? First of all, we must understand one thing. Existence of us has nothing to do with how physics works, how chemistry works, or how the universe operates. We are just observers for that matter. Yet for our knowledge of physics, our knowledge of biology, our knowledge of chemistry is all depend on our ability of observing phenomena and understanding their inner workings in terms of mathematics. Unless we observe phenomena and understand their inner mechanics in terms of mathematics, that physical phenomena or that chemical phenomena will keep working with or without us. So in order to understand these phenomena, we need to recreate them under controlled conditions. First, we have to observe them in nature. Then we have to recreate them in our laboratory conditions. What we do to understand this big puzzle, of course, our laboratory, AECL, Atmospheric and Environmental Chemistry Laboratory, works on one little component of all this giant picture, which is reaction mechanisms. Of course, atmosphere forms with hundreds of thousands different species of molecules. Quite guesstimation numbers, all our atmosphere contains 5.2 times 10 to the 19 tons of gas, which means 52 and 18 zero after that. That many tons of gas is above you, left and right, and all over you. Another interesting number that how you are linked to this atmosphere is environment. For the listeners, have a guess, for example, how many liters of gas that you are filtering daily within 24 hours time, how many liters of gas that goes into your lungs and comes out? Let's think about it a little and I'll give the answer in a little while. But this number proves that what our understanding of environment is not buildings and earth and whatever around us. The greatest component of environment is the gaseous component that you keep filtering in and out, in and out. So quality of that environment is so important. And that phenomena works on the basis of reaction. Reactions are keeping that phenomena going, and especially the oxidation reactions. This is our laboratory. These pictures are taken in the laboratory of Manchester University. Of course, we removed these laboratories into Tarla. Now they are getting set up here. I guess you may have one picture of the mass spectrometry laboratory later on that's being set up here. That mass spectrometer instrument that you are seeing on the left side of your screens is linked with a flow tube device where we created reactions isolated from the atmosphere, and we interact chosen desired molecules with each other under total control of temperature, contact time, which means how long those selected molecules are spending together, pressure and humidity, and so on and so forth conditions. If we need, we can create unstable molecules for our interest time period. Of course, by re-experimenting these conditions with different temperature and pressure profiles, then we at the end come to calculate reaction rates of individual reactions, which may well be millions and millions possible within our own atmosphere. For the mass spectrometry laboratory, we have two collaborators. One of them is University of Bristol. The other one is JPL, Jet Propulsion Laboratories, NASA in California. These people, the Professor Carl Percival and Professor Dudley Shallcross, are my PhD supervisor and my external examiner of my PhD. We are still working together. In our second laboratory, we are building and improving an ultraviolet photoelectron spectrometer. This spectrometer is totally home built. Almost 70% of it is built by Professor John Dyke of Southampton University and was inherited to me. Professor John Dyke is the only developer of these instruments in the world in terms of science for gas detection. Such instruments of electron spectrometers are being used in different radiation energies, such as X-ray and whatever, for surface science studies. Yet there is no photoelectron spectrometer yet is being in operation to understand gaseous species and their interaction with each other. We need higher sensitivity to resolve this problem, and we are working to improve our molecular sensitivity on the UVPES system to build first gaseous reaction rates experiments being performed in a photoelectron spectrometer with a photoelectron spectrometer methodology. Hopefully this may give results within a year or year and a half. So after you see all those instrumentation and talk about the atmosphere, of course you may be thinking how these are related and how they are working all together. The general science discipline works this way. If you have a question on hand to answer, you need to do an operation that consists of three different operations. One of them is the field observations, that this phenomena, how it works under natural conditions, that you need to understand that with field observations. In our case, this could be research ships that are traveling in the world's oceans. This could be a research aeroplane, which are flying over tropospheric and stratospheric conditions. Might be high atmosphere balloon flights that we are installing our instrumentation to very large balloons and send it to higher atmospheric levels. Or it might be your city, corner of any point of your city, that we would be measuring how dirty the city atmosphere is, what the effects of traffic might be injecting into our own atmosphere via combustion operation, of course, and combustion of benzenes are quite complex chemistry overall. Anyways, which could be on a mountain that we would be watching a volcanic eruption, what kind of chemical composition coming out. It could be a rainforest that we would be measuring, or the top of rainforest, that what kind of chemical composition coming into our atmosphere. Then with that information, we isolate those reactions, interest reactions, into laboratory conditions. So we can perform those specific oxidation pathways, specific dissociation reactions, or specific 2 or 3 body reactions from the second order, how they work under different pressure and temperature conditions. Of course, once we have experimental results, dependable experimental results, those results are being used in very big simulation models of our atmosphere, which we call these giant simulating softwares, global atmospheric models. Even the individual reaction rate information goes into those models, which I've shown in the second slide, the complex system. Of course, there are other scientists trying to understand how the clouds work. There are other scientists trying to understand how the radiation dissipate in through atmospheres. There are other scientists trying to understand how the aerosols behave and what the cross chemistry on the surface of the aerosol with the gas phase. It's a very complex, deep field that extends. But each of us are feeding small information into these global atmospheric models. Then we would be able to model the phenomena of atmosphere with our best knowledge of mathematical relations in between of these tiny contributors of the whole complex phenomena. Of course, while doing this, especially from the relation of field studies and laboratory studies, we do develop our own instrumentation because we come across with special needs. How to operate your mass spectrometer in a research aeroplane is a different question than your scientific question you have it in the laboratory, or how to operate your mass spectrometers on a rainforest conditions of 98% of humidity and 48 centigrade degree heat, or in a research ship that travels at -36 in northern Atlantic Ocean. So these are all different needs or all different conditions that creates special needs for you to design and overcome the problem. I'd like to introduce my own research project here shortly and our instrumentation that we are using in our laboratories. And also this might be a slide that is explaining how to build a research project or proposal idea in one's head. First of all, of course, prior to this project, I have been working on atmospheres, specifically troposphere and stratosphere. The oxidation mechanism, how the oxidation mechanism works. By the way, oxidation mechanism is the cleansing mechanism of our atmosphere. Every organic molecule or volatile organic compounds that mix into atmosphere, they start their decomposition with an oxidation reaction. So understanding oxidation reactions are so important to understand how our atmosphere operates in terms of cleansing, in terms of cross chemistry, because not every pollution is immediately dangerous or bad. Some of them becomes extremely bad or very dangerous after the first or second reaction of oxidation while they are breaking down. So in order to have a sound and strong research project, scientifically sound and strong research project, first you need to understand the details of the large phenomena that you are working on. You need to be expert. You can't just thought of, oh yeah, maybe I need to work on this question. Most probably that question has been answered many times in history if you are developing your project ideas this way. First, you need to know the discipline of science that you are creating project for in very great details. Then second of all, your technical ability and knowledge is so important. Without appropriate instrumentation and appropriate observational capacity, you cannot understand the phenomena. That's where accelerators are becoming extremely important. If you like to have a look at the reaction in details, you may either need to have extra information from the molecule or even deeper states of electronic structure. In order to delve into these kind of details, you need high energy and high intensity.
Dr. Bacak, do you hear me? You have only 5 minutes.
More details in that picture. That's where the accelerators come into play. Very important.
Bacak, do you hear me?
Yes, I can hear you, sir. Is there a problem?
You have 5 minutes to complete.
I have been, let's start it late, sir. So I need 10 minutes to complete.
Okay.
So thank you very much. In order to create this base for the project of oxidation capacities, we have referred to the work of Newsom and Evans, 2017. Newsom and Evans studied 5 different global models in terms of reaction kinetics tool sets. And they realize in our understanding of oxidation reactions, we have a great gap on experimental work. They have shown on the bottom left-hand corner of this slide, our experimental knowledge error margins are going extremely large, especially in negative temperatures, because around those values, there are no experimental work that's being done in the laboratory. More experimental work gives us a better error margins. So this improves our uncertainty levels of our large global scale models. Uncertainty is a very important value for many of the science problems. In order to decrease this uncertainty, we need more laboratory work to be done in our laboratories. So we have employed our flow tube instrument. This is our schematic diagram of flow tube instrument that we create different molecules and inject different molecules from different inlets, and we let them meet with each other for a known amount of time. Then they react. Following the reaction, we ionize them and we send them into mass spectrometer system. And by using Genius's work of Arrhenius equation from Svante Arrhenius, we relate the temperature and the reaction rate to each other. And by performing the same reaction under different temperature and pressure conditions, we calculate or we observe if there's a temperature or pressure dependency of that special reaction, and if there are any transitional states, molecules of that reaction. As well as doing experimental work, we are performing very complex computer simulations. This is my master students Damla Atakent's work for our upcoming experimental work. What you are seeing here some very complex molecules of halogenated monoterpenes, which are byproduct of red algae in Southern Pacific Ocean that mixes into atmosphere, and it affects the atmospheric oxidation capacity up to 16%. So the algae that you don't even know that they exist, they are affecting your atmosphere. And how they are affecting the atmosphere, the very important pathways of, first of it is reacting with OH and reacting with oxygen. They are increasing the oxidation, decreasing the oxidation capacity of whole atmosphere. If you are oxidizing these molecules instead of other molecules, your oxidation capacity is decreasing. So our upcoming project, following our recent paper with Bristol University, NASA, University of Ankara, Tarla, and South African universities and South African Meteorological Office, that we have decided to work on or target to deploy our observational instruments to the research ship of South African Science Council, that you are seeing the ship's picture on the right-hand top corner, that called St. Agulhas II. We are planning to build an instrument consist of mass spectrometer, some gas analysis instruments of ozone, CO, and NO and NO2, NOx that we call. And also, if we may manage to get a Fourier transform infrared spectrometer, we will combine all these three instruments in our Tarla laboratories and deploy these instruments to St. Agulhas II for a long field campaign of detecting halogenated monoterpenes. So this would be another project following 2232, an international level project that we are targeting off. And also with this project, we are expanding our work area of atmospheric and environmental chemistry laboratory into the ocean and atmosphere relations too. Then I would like to talk about our second expanding project of higher atmosphere levels. Higher atmosphere is a very important part of the general atmosphere, but it's very understudied. There is a special group from Leeds University, Professor John Plain, has been the only name of this subject. He was the pioneer, of course, almost. And AECL now is planning to expand their research effort into this area of exosphere and thermosphere research. And there are some very important metal ion reactions that we are now doing our modeling studies for these metal ion reactions as well to perform in our flow tube system. What you are seeing here is our prototype experimentation. I will not be giving so much detail about that, but current discharge ionization source is a new method of ionizing molecules without using any radioactive source or any other non-mobile sources, that you can operate this source with the electricity under any conditions, because as you have understand, the field efforts have very important problems with laboratory instruments. So we need to develop this kind of an ionization method that we can use it anywhere just by electricity. I'd like to talk about very shortly our activities, our possible activities of our laboratory. As you have seen, that we have been doing many different works in the laboratory by using our analytical knowledge. Because you're able to understand molecule and the properties of molecule, either by taking an electron out of their valence orbital, or by looking at the weight of that molecule, they understand many information, lots of information about that, the source, the fate of it, how it's going to live, what's going to happen next. So by using this information, we are actively working on different projects upon Arctic and Antarctic polar science, climate change, global warming. These two are quite different things, by the way. They are maybe linked in terms of ozone and oxidation, but they are quite different two phenomena. Health and pollution, of course, they are related to our air quality in our cities are totally dependent on reaction kinetics, and how we mitigate the sources, pollution sources in the cities is directly related to air quality of the cities in terms of pollution. And of course, this relates to health too. Defense and security, if you do know, or if you can understand where the source of the molecules are, you can detect explosives, IEDs. This is a great advantage because especially terrorist activities are generally hidden bomb actions, whatever. You can trace drugs, you can trace human trafficking through your borders. You can understand what kind of activity going on inside the closed areas, such as buildings, rooms, caves, so on and so forth. An incoming very important subject is indoor chemistry. We haven't studied indoor chemistry much in the classrooms, for example, in the hospitals, for example. We have studied outside chemistry quite a lot, but the indoor chemistry is quite important too. And at last, planetary atmospheric and reaction kinetics. Why planetary? Because if we are to leave this planet, which we need to one day, because our sun is going to stop burning. And if we are still here at that time, that's the end of humanity for sure, if there is nothing happen prior to that. But if possible, we'd like to leave this planet, live and go somewhere else. In order to do that, wherever we are going or wherever we are targeting to go, we need to understand the inner workings of the atmosphere as well. Because we take 10 to 14,000 liters of gas every day. So 10 to 14,000 liters of gas goes into your lungs and comes out. Imagine any other ways of filtration. If you are drinking 10 liters of polluted water, if you are eating a kilogram of polluted meal, so this is 14,000, 10 to 14,000 liters of gas goes into you, it gets filtered inside you and comes out. So publications that we have publicized during the last 18 months. And these are my international collaborators and my institute that I'm working in right now. Thank you very much to all of you. I hope you enjoyed it. If you have any questions and comments, I am ready to note and answer if possible.
Okay,
thank you very much.
Thank you very much. Do you have any question or comment about the talk? Okay. You have? Oh, okay. Dr. Bajak, we have no any question from room.
Thank you very much.
Thank you very much for your nice talk. See you later. Okay.
Thanks a lot.
Okay. Saverio Bracini from Universitat Bern, Switzerland. Ha. Seviyorsun da şeyde ekranda görünüyor mu? Görünmüyor mu? Sen yardımcı olursun. İzleyenler. Son konuşmacımız login olmuş görünmüyor. Gökhan hocamız onunla temasta. Eğer sunacak olursa yarın programda bir yer vermeyi planlıyoruz. Okay, we are finishing today's sessions. Hope to see you tomorrow morning. Good evening for all you. Thank you for your participation.